Okay, so in the last class probably we have discussed about SSB, of course suppressed carrier. So we started already exploring modulation technique which are bandwidth efficient. So we have already shown that whenever we do a modulation in VSB-SC, we have shown that whenever we do modulation, basically the bandwidth gets doubled. And because in the baseband of the spectrum symmetry in the positive and negative half, the doubled bandwidth will have a upper sideband and lower sideband which are just mirror image to each other. So means immediately it is clear that we do not have to transmit that whole information. The information is already contained in one of the sideband. So either upper sideband or lower sideband. So it will be good if we can just transmit one of the sideband and somehow devise a technique where we can modulate in such a way and also we can demodulate it. So this was our target, right? And in that process we have shown that yes, it is possible. It is possible through a transform called Hilbert transform. So if you do Hilbert transform, then you can represent this particular signal as some MT cos omega ct plus MHT sin omega ct. Of course, it is plus or minus. So accordingly, you will be getting either lower sideband or upper sideband. So that is actually we have proven from the spectrum that if we have SSB-SC signal that can be represented as this, where this MHT is nothing but the Hilbert transform. That means MT passed through a transformer which is the Hilbert transform, and we get MHT correspondingly. Okay. So that is what we have already shown that this is possible. So all we have to do is take the signal, do a Hilbert transform, multiply the original signal by cos omega ct and the Hilbert transformed signal by sin omega ct through a adder, either add or subtract. Accordingly, you will get your overall representation of upper sideband or lower sideband. Okay. So this is what we have already shown. That is one way of defining it, but we have seen the Hilbert transform is not that easy to realize. What we have seen that actually the Hilbert transform is almost like it keeps the amplitude same. So whenever it passes through that transformer, it keeps the amplitude same. For phase, it gives for every frequency component, it gives pi by 2 phase shift. That is something we have discussed that which is difficult to achieve. Okay. So that is why we have devised another method which is called Weber's method, which is selective filtering method. That means we just do the filtering, do a modulation in such a way that in the low we put a low pass filter at the low frequency domain, we can do the filtering and then we can translate it to the frequency where we wish to put it. Okay. So that way we can generate this kind of signal, but for that we require that the signal has 0 component or 0 power around the frequency 0. Okay. So that means no DC value and around that nothing is there, because that is where the filter roll off can be put over. Okay. So that is required. So there are two methods to actually modulate or generate SSB signal. This is something we have seen, and then for demodulation it is pretty easy. We have seen that also, that this particular signal, that phi SSB-SCT that we have got, you just multiply this with a cos omega ct. Immediately you will be getting a term which is related to baseband of that signal, and then there will be terms of higher frequency, cos 2 omega ct and sin 2 omega ct. You put a low pass filter, those things will be rejected, all those higher frequency terms you can extract your MT. But for that you have to remember that I need to have a local carrier, okay, which is completely asynchronous in phase and frequency with respect to the incoming signal, carrier frequency and phase. That is absolutely required. We will try to see whether that is possible or not. Okay. So this is something we have discussed so far. What now we will like to discuss, that is there any other demodulation technique that is possible in SSB-SC, or I should not say SSB-SC, is there any other demodulation technique if I add carrier to it? Okay. So all we are trying to do now, we are calling this as SSB signal, that means no suppressed carrier. So, we will be adding carrier to it, A cos omega ct and the original SSB signal, which is, if my message signal or modulating signal is MT, so MT cos omega ct minus or plus, depending on whether upper sideband or lower sideband I am taking, MHT sin omega ct. This is the representation of SSB. I am just adding carrier to it. At the transmitter end, I can always add the carrier, because that is where I have the local carrier with which we are modulating it. So, I can always add the carrier to it. Okay. So, this is what I will be now transmitting through the air instead of just transmitting SSB. So, that is why we are calling it SSB, only SSB, no suppressed carrier. So, carrier is already over there. So, that this particular signal I can re-represent as A plus MT cos omega ct plus or minus, I am just taking one of them. So, MHT sin omega ct. Okay. So, it is a cos term and a sin term. I can represent these two terms as another some amplitude, let us say Et into, let us say, cos another theta t, whatever phase that is, that might have some frequency term, phase term, whatever it is, overall phase. If I just say theta t, I can always write that this is my cos, means Et cos theta t, and this is my Et sin theta t. I can write that way, and then immediately I will be getting another cosinusoidal term, that you can already see that the way I represent it accordingly, I will be getting another cosinusoidal term, of which the amplitude will be this square plus this square, right, means that Et square. Okay. So, whatever that Et, so this I can write as Et cos theta t, and this, let us say I write Et sin theta t, I can always write that. Whereas, what will be the Et? So, if this is equivalent to this is equivalent to this, if I just square this and add, that should be Et square. So, therefore, Et square should be A plus MT whole square plus MHT whole square. Okay. So, what does that mean? That means that same signal I can actually represent as a cosinusoidal signal, and this Et becomes the envelope of that cosinusoidal signal. That means, it is a cosinusoidal signal whose amplitude is varying with time. Now, it is no longer a constant term, it is a time varying amplitude, similar like DSB or amplitude modulation we have done. So, there was a means carrier, and the amplitude was modulated, right. So, same thing is happening over here. So, Et is the envelope which is carrying that message signal in some way. It has a term which is equivalent to this mathematically, and of course, there will be a phase associated with it, theta t, but I am not bothered about theta t right now, because what we are trying to do, because we have added the carrier, we want to actually do envelope detector. Okay. So, carrier detection we have already seen in amplitude modulation, we could add carrier in such a way that with some condition that the carrier strength should be at least bigger than the lowest amplitude, okay, modulus of that. So, we have trying to employ the same thing, we are adding carrier hoping that we can do same thing. There it was very simple, it was just something into cosinusoidal. Here we have constructed that cosinusoidal, because we want to just track the envelope of that cosinusoidal, that is what we are trying to do. So, now let us see if the envelope detector gives me the signal back, that is what we are trying to do. So, if that is E square, then what is Et? Because this is the envelope I will be detecting through a diode detector. If I just pass it through a diode detector and then charging, discharging the way I have designed it. So, if I just do that, that should be square root of A plus MT whole square plus MHT whole square, right. So, this I can further write this to the power half A square plus 2 AMT plus M square T, sorry, m square t plus mh square t. Okay. I take a out, so a square out, because there is a square root, so it should be a. So I get 1 plus 2 mt by a plus m square t divided by a square plus mh square t divided by a square to the power half. Now I will try to put some approximation, okay, means where I can actually detect mt. So I know that the square terms are bothering me, so I need to somehow take this out. When I can neglect this, if mt is much less than a, and also you can see Hilbert transform, what it does, every frequency component it actually gives the same amplitude. So if mt is much less than t, I can also write mht, that should be also much less than a. So this is something I can write, because in the amplitude of Hilbert transform, means in the transfer function, the amplitude actually gets translated with unity gain, every frequency component. So I can write this safely. If this is the case, then what will happen? This quadratic term I can neglect if this is happening, mt divided by a. And you can also see, because I want to put this, that is why I have taken out a. Okay. So approximately this I can write as a 1 plus 2 mt, so the linear term remains and all other quadratic terms are ignored. Now what I can do, again I can do another approximation, because mt by a, again I know that all higher order terms can be neglected. So this to the power half I can put in Taylor series, okay, and all higher order term starting from quadratic to cubic and all those things I can neglect, and this will be approximated as a 1 plus, there will be a half factor coming because the second term will have half. So this 2 will be cancelled, I will get 1 plus mt divided by a. Okay. So that is again approximately this. Immediately you can see this is actually a plus mt. I just have to put a DC blocker and I get my mt back. So the condition is in SSB also like AM. See, DSB had a version AM where I was adding carrier, right, and with carrier I was able to do my receiver very simple, or do my receiving very simple, in a very simple way. So I was able to do that. What I was doing, I was just putting envelope detector followed by a DC blocker. Same thing I can do over here, but there is a condition. For AM also there was a condition, right, that modulation index has to be just less than 1, or I need to say that this mod of mt, okay, at least the negative part of it and modulus of that must be less than a. This condition has to be satisfied always. Okay, I was having this condition less than equal to. Now I have a condition which is much more stronger. What does that mean? We have already seen that this was when it was taking equality with the tone modulation. We have proven that at that time I had the energy efficiency which is 33%. Anything more or mu lesser than 1, the energy efficiency will be lesser and lesser. Here what is happening, I need to choose a which is much bigger than mt. So therefore the modulation index corresponding to this, or I should say energy efficiency, which will be much more watts, because I have to really put very strong carrier. So I am just wasting power by putting a very strong carrier, because otherwise I won't be able to detect this. Okay. Because for detection I have already seen mathematically I need to have that approximation. If that is not there, all quadratic term and cubic term will be coming into picture, and that will actually distort my signal. Okay. So on top of mt there will be m square t and m cube t and all those quadratic, all higher harmonics terms will be coming and mixing with the signal, that will distort my signal. So I cannot really afford to do that. If I wish to detect, I need to have this condition, and immediately the power efficiency goes away. Okay. So basically, as we have stated that there are no free lunches. SSB, it is a bandwidth efficient scheme, that is very nice, but in SSB if you wish to do the receiver technology little bit simplified, then you have to add carrier, and that carrier strength or carrier power has to be very high. So you pay in power as penalty, right, and later on when the carrier recovery circuit will be designing, you will also see for SSB and the other version VSB that we will be discussing probably later on, you will see that for them carrier recovery is almost impossible. You cannot really do carrier recovery for this bandwidth efficient schemes. It's very hard to do that. Okay, we will prove that. So if that is not possible, then definitely we have to take this particular thing where we don't suppress the carrier and immediately the power efficiency goes for a toss. Okay. So we have two options, either you make it bandwidth efficient but then power efficiency will not be that good, or you make it power efficient then bandwidth efficiency will not be that good. So this is what we could see. So far we have discussed something about single sideband. Now in single sideband we have also talked about that it is only good if you wish to really do the receiver circuit, transmitter circuit a little bit simplified like the waiver circuit, okay, where you can just put filtering approach. For that you need to have a spectrum of the modulating signal which is devoid of any component around DC, okay. So that is pretty much required, but we have seen that for voice that is true. Fortunately this was happening, so people could employ SSB in voice, but for video the spectrum looks like this. So there are strong term around DC value and you cannot ignore them, so that is not possible to ignore this. If you ignore that, probably signal will be distorted. So you are not, means for modulation you cannot really distort the signal, that is something is not allowed for modulation. So if this is the case, SSB is almost impossible. We have said if we wish to do it through filtering, that filter should run like this, sharp cutoff which makes it non-realizable in reality, so it will not be stabilizable, right. So what is the technique that we should employ? So here we will probably do a compromisation. We will take some amount of bandwidth efficiency, means we will compromise on bandwidth from SSB, but also will gain little bit on power. We'll show you that, demonstrate you that. Okay. So that's the VSB-SC. That means whenever we do VSB, so if we just demonstrate, suppose this is my MT and corresponding MF which has a bandwidth B. If I do DSB, then at FC and minus FC this will be modulated and it will occupy band from minus B to, means FC minus B to FC plus B, so almost 2B bandwidth, right. If I do SSB, then I will be taking, if I take upper sideband, I will be just taking one of the sideband, the upper one, okay. So this is at FC minus FC, again this is B, so it is bandwidth efficient, instead of 2B it is this. And because I cannot create this, if something around 0 is already there, what I will be doing, I will try to create something which is like this. Okay. So basically what I am trying to do, I am trying to suppress some portion in my valid band of USB and I am including some portion in the LSB, okay. And with that I am not including that whole band, I am not running up to B, it will be somewhere, it will be ended. So my overall bandwidth will be this much, let us say 70%, 75% of the overall 2B. So I am benefiting by saving 25% of the overall band, okay. Whereas from SSB, compared to SSB, I am taking extra, let us say band, okay. So this is what I will be trying, and if I wish to do that, the corresponding filtering you can see that might have a nice roll off, because I do not have to do a sharp cutoff at that frequency. So this is called the VSB, or we call it vestigial sideband, okay. It's little bit distorted sideband we are taking, and we are actually taking a mix of both sideband, both were distorted, but you will see that will in such a way we will design the filter so that we can actually get back the original signal, right. So basically what we are trying to do is something like this. again we will employ the same SSB technique. We will try to appreciate it because it is being appreciated at the frequency domain. We will try to appreciate it from the frequency domain and then go back to the time domain characteristics. Okay. So, it is actually nothing but the modulated signal means, or we can say the VSB-SC, that is the modulated one, followed by a band pass, or sorry, a high pass filtering. Okay. Either high pass or it can be a band pass also, you can end it later on. So, the upper one, it is not a problem, anywhere you can end. Only the lower part, the filter has to be properly designed. Okay. So, we can say it is modulated signal, let us say, which is MF plus FC and MF minus FC. This is just the spectrum of VSB-SC, followed by a filter, okay, filter transfer function. The filter transfer function, we know that it has a either high pass or we should say band pass characteristics. Okay, it might be high pass, we can just run it, start from here and run it for the entire these things, but later on we will also understand if we try to do that, probably that is not really required. We do not have to really include that entire band. So, what we can do, we can just end it somewhere. So, we can just put a band pass filter with the typical characteristics. So, this band pass filter we are defining as HIF. Okay. So, basically to generate my VSB signal, all I have to do, I have to modulate it followed by a band pass filter, right. Now, let us say I need to, so this is my modulated signal. After modulating, I wish to, because VSB and SSB almost looks like similar thing. So, what I wish to do, my demodulator should be almost similar. If I do not add carrier, so it should be something like this. This modulated signal, it will be transmitted over the channel, and then at the receiver I will first through antenna I will take that, I will multiply this with a cos omega ct, okay, followed by some low pass filtering. That is what we do, because whenever you multiply there will be a baseband term as well as some high frequency term at 2 FC or minus 2 FC, you want to reject them. So, followed by a low pass filter. So, same technique I wish to employ, okay. But while employing them, I need to understand what kind of low pass filtering I will be putting, so that it is consistent with this HIF which I am putting, that band pass filtering I am putting at the transmitter, and I get my signal back. That is what I am trying to do now. So, what I will do, suppose corresponding to this signal I have VSB T, okay. So, it is just the Fourier transform or inverse Fourier transform of this, okay. So, whatever this is, right now I am not bothered about it. So, my detection or demodulation will be, suppose it is after multiplication I will get this ET. So, that should be phi VSB T multiplied by a cosinusoidal. I am just deliberately putting a 2, amplitude 2. So, that is just a constant, it does not matter. You will see that this 2 is required, right. This is what I wish to do. So, immediately the frequency domain, how it will look like. So, if I just try to plot EF, how this should look like. So, that should be phi VSB, now 2 cos omega ct if I have given. So, it should be plus FC minus FC. So, this should be F plus FC right. So, this is what we get after modulating this. Now, what we will do? We have to follow, means pass this EF through a low pass filter. So, let us say that has a transfer function of HOF. Okay. So, then whatever E dash F I will be getting, that should be this phi VSB signal or this multiplied by cosinusoidal, that must be passed through this. So, that should be VSB F plus FC plus phi VSB F minus FC multiplied by HOF, right. And what do we expect? And if I design my HOF correctly, this should be my MF, right. So, I should get my signal back because I am doing the demodulation. So, in the demodulation I will be getting my phi VSB like SSB or DSB, I will multiply by cos and then put a low pass filter, I should get my signal back. That is what I have done for all other modulations. So, same thing I should expect over here. Okay. So, that should be MF. Now, phi VSB, I already know the characteristics, right. So, that I will put over here, and also I am aware that this is a low pass filter. So, any higher frequency term that will be created, low pass filter will be able to reject them, right. So, let us try to put that. So, what do we get? I will get, so let us just in this phi VSB f plus Fc, let us replace by f plus Fc, and for f minus Fc let us replace f minus Fc and put it over here. That is all we will be doing. So, that should create m f plus 2 Fc if I am considering f plus Fc, and then the next term which is m f minus Fc, then f minus Fc plus Fc. So, that should be mf followed by h I, it is f plus Fc because it was f. So, it should be f plus Fc, and the other term should be m f plus Fc minus Fc. So, that should be mf plus m f minus 2 Fc and hi f minus Fc, right. This is this EF part, okay, just by replacing this over here. Okay, so, this is the EF part. In EF I have just substituted this, and wherever required in place of f I have put f plus Fc or f minus Fc, and I have substituted it. That multiplied by HOF must give me MF. This multiplied by HOF, but now we have to see whenever I multiply by HOF, then some of the higher frequency term will be cancelled. Look at this term, where it is going. It is actually MF shifted by 2Fc in the negative half. So, this must be cancelled because this is followed by a low pass filter. So, low pass filter must cancel this. Same thing will be happening over here, this must be cancelled. So, what will be left with is M f hi f plus Fc plus again MF. So, I can take common MF plus hi f minus Fc, right, into HOF must be equal to MF, because that must give me, after passing through low pass filter, I must get back my signal. So, that is the condition. MF gets cancelled, I get a relationship between my input filter and the output filter, or I should say filter at modulator and filter at demodulator, I get a relationship among them. So, I can just write my output filter should look like this, sorry. Right. So, that should be the output filter given the input filter. Okay. So, this is the relationship which will be happening. Okay. Now, what we will do, we have just created a relationship between the filters. We have still not seen how the VSB will look like, means how do we characterize this filter. So, all those things we will do in the next class. Thank you.